Well, hello, physical geology students. Welcome back this time to our discussion of plate tectonic theory. And I'll just say it's really important that you spend some time looking at the resources, read the chapter in the text, really try to understand this because plate tectonic theory, even though we didn't start off the semester with this, we're now through, we're now a little bit into the semester. It's really important that you have a good foundation in this because we interpret everything through plate tectonic theory. And of course, before plate tectonic theory, which really emerged in the late 1960s, geologists interpreted things largely very differently. So it's amazing, of course, as a paradigm within the science of geology, just how powerful plate tectonic theory really is. So this landscape you see on the slide background is one that you would look at and see the mountains and see the valleys, and you would start to think about how this landscape got this way, partially through the transport of materials from higher elevations to lower elevations via wind and water and so forth, or various erosional processes. But initially, those mountains were created somehow, and the basins were created somehow, and that all comes back to plate tectonics. Then all the storyline the development of this theory actually begins many, many, many years ago, when somebody noticed on a globe that the continents kind of look like they fit together like a jigsaw puzzle. And I think most of us in our childhood days, when we looked at a globe, probably saw something similar to this and said to ourselves, interesting. It looks like South America fits into the armpit of Africa. And I say armpit of Africa just because it's kind of shaped like an arm, okay? Not anything more than that. But South America looks like it fits in under Africa's arm, like a football, kind of running down the field with a football or something like that. Anyway, of course, when you're looking at just the coastlines itself, the fit isn't perfect. Perhaps the fit's a little more perfect when you look at the continental shelves. And indeed, Alfred Wegener, who did look at the continental shelves, then was able to come up with his idea of continental drift. Alfred Wegener was a guy, though, who had a reputation for being relatively unconventional. He's one of these people that like to question things, that were always, whatever the status quo was, he was interested in. He was a true scientist, really interested in exploring big questions. And of course, whenever you're questioning the status quo, as you probably all know, it can get you into trouble. So anyway, the 19-teens and 20s, the idea of continental drift was finally put together. He published the idea after studying existing literature, had a long list of evidence, including the shapes of the continents, but also including a variety of rock evidence, mountains, glacial formations, fossils, all from both sides of the ocean that were similar. Specifically, organisms, there were certain specific organisms like mosasaurs and so forth, that were land-dwelling and could not have swum across the ocean to be deposited both in South America and in Africa, for instance. Also, glacial evidence in very warm places like Africa and India and Arabia. How do you get glaciers in a place that's very near, that's in the tropical area or very, very hot in general? But he had no mechanism for how the continents separated the way they did. Thus, he was ridiculed, not given a lot of respect for this idea during his lifetime, ended up dying on an expedition to Greenland in 1930, and the rest is history. This kind of thing, he's not the only person to ever have this happen to him, and he won't be the last. But it's one of those examples of where, keep your life in perspective. You may have a really great idea that right now is kind of thrown around as idiotic, but 15, 20 years from now, and you may already be dead, that idea may become really important. So sometimes ideas live on beyond the individuals who first proffer them, and it's important that you can to remember that you can live on like that, just as Wegener has. Every geologist, everybody who takes an introductory geology class learns about Alfred Wegener, and who would have thought back in those days? Anyway, so this is an example of some of that fossil evidence. So we've got some organisms that can be found on both continents or across continents for that matter, in terms of the Glossopteris ferns and so forth. These are classic examples. Other examples, of course, here's the fossil evidence again. We've also got examples of environmental evidence, placing a lot of areas down near the equatorial regions or warmer than they really are. The present day, of course, looks like this. We have areas that were all connected to Antarctica at one time where you can find similar stuff going on in terms of the rocks and whatnot and glacial features. So these are all really important pieces of evidence. So later on, of course, in the 1940s and 50s, we began making maps of the ocean floor, and those maps were made through sonar surveys. We were looking for German U-boats, is what it really came down to. But in the midst, all this data was collected, and then, of course, it became used secondarily by scientists. And, of course, this kind of thing happens all the time, where you take a piece of, or a big, huge data set, and you reuse it because it happens to have really good information for other things. And this sonar data became just such an example. What was discovered down there on the seafloor were mountain ranges, valleys, trenches, plains, and all kinds of other things. And it happened to be a woman who created, actually Bruce Heason got all the credit for the most part early on, but Marie Tharp ended up being she was the one who actually did all the work. So the number crunching and so forth. And they plotted this map of the ocean floor by hand. And here's a picture of her at work, actually. And you can see the immense detail and what she's working on. And here's some of the data she's looking at. And this is, of course, a topographic profile. And you can imagine having to take thousands upon thousands upon thousands of such profiles given certain coordinates and having to reproduce what is a three-dimensional landscape in this massive 2D globe. The most detailed maps of the ocean floor. What it essentially did was reveal a whole new world that we didn't even know existed. And here's just some fun things. Here's some examples of her with, I think that's Bruce Heason. I'm not entirely sure, but it's certainly Marie Tharp looking at her map with somebody. Yeah, that looks like Bruce. I actually don't know much about Bruce Heason. I probably should, but I don't. As much as I people hear about Marie Tharp, because again, she did the work. So paved the way for the acceptance of plate tectonics and continental drift. But interpreting what all that new physiography on the ocean floor meant was a whole other thing. And it took some other individuals, Harry Hess for one, to suggest that the mid-ocean ridges in particular, if we go back to to this map here, you see these ridges down along the mid-ocean, middle of the Atlantic. His idea was that these mid-ocean ridges were actually plate production factories. And then he used paleomagnetic evidence, looking at magnetic anomalies in the ocean floor, which produced these stripes that were parallel sets of stripes on both sides. And the lab you're going to work on this week online is actually going to deal with this. But anyway, these are when the molten material comes up with these divergent boundaries, like the Mid-Atlantic Ridge, which we didn't realize was divergent at the time, but this is what he was suggesting. When the iron-bearing minerals cool, they lock in place and record Earth's magnetic field direction. And every now and then, because the Earth's poles reverse, that's been in the news lately, polar reversals and so forth. Of course, it probably takes thousands of years for a reversal to happen when north becomes south and so forth. The magnetic minerals align with the current magnetic pole direction. So we have a record of magnetic pole movement, but we also have this back and forth reversal, which allows us to prove that these were divergent boundaries. And of course, the ocean floor has also been dated now along it. We know exactly how old the ocean floor is from one coastline to another. This is a great little animation just showing you the movement over the last 50 years of the Earth's magnetic pole. This little dot is the geographic pole. That doesn't move. It's stationary. It really is kind of a meaningless pole for the most part. It's the magnetic pole that your compass is interested in. And this is the one that minerals are affected by, so the iron-bearing minerals and so forth. So this is an example of some of that magnetic striping, and you see all these different colors. These are all magnetic data. But if you look at the Mid-Atlantic Ridge over here, you can kind of get an idea of what it looks like on both sides, and both sides are mirror images of each other. If we look a little more closely, we can see this again at the Mid-Atlantic Ridge. All right, this is some of the actual data. Over here, you can see what they've done is they've colored. This is along the Juan de Fuca boundary, so you can see the plate boundary, transform boundary, plate boundary, and so forth. Transform boundary, and you can see the orange on both sides is the same age because it's a spreading center. So materials coming up, pushing the two plates away from each other. Meanwhile, the entire Pacific plate over here is subducting beneath North America over here. But the orange layers, the orange rocks are the same age, the green are the same age, and so forth. These are the oldest. These red are the youngest, and hence the scale here. So the way this actually works, of course, we can send a magnetometer out behind a ship, and then the magnetometer can detect the mineral position. And if you do this enough times back and forth over the ocean, you can start to pick up the magnetic anomalies, and we get to get an idea: positive, negative, positive, negative, positive, negative. I mean, the ocean floor visually is not striped, but magnetically it's striped, and you get something that looks a little like this. Okay, so that became very important. And then dating these, noting that they get older on both sides, going away from these ridges, was very critical as well. So as these mid-ocean ridges spread, the minerals are going to lock in position around the ridge, and then as new material comes up, those areas that had locked in position move away on both sides, and you end up with the stripes. So again, positive, negative, and of course, both sides of the ridge are essentially mirror images of the other. So you end up with, you can also then, of course, determine the age of the seafloor. And we know that the oldest seafloor is about 185 million years old. And actually, some of the oldest is right along the coast of Africa and the coast of North America, and then out here in the Western Pacific off the coast of Japan and so forth. But otherwise, the ocean floor is quite young. And I said the oldest was about 180 million years old. Well, that's significant when you think about the fact that the continents themselves take the Canadian Shield at 3 billion years old. So the continents are made of cratons that are made of rock that are much, much, much older than the ocean floor. I mean, that's exciting stuff. What that means, of course, is that the ocean floor is constantly being recycled. And it's being recycled almost on a scale of a 200 million year cycle. So, the oldest floor is just under 200 million years old, and that's really, really important. So as subduction occurs, like it does around the Pacific here, and will eventually begin again around the East Coast, probably about 100 million years from now, all this old stuff will get recycled, and it's very dense anyway. As the crust gets older, it actually becomes denser and sinks isostatically, so to speak, deeper within the asthenosphere, and will sit there and more easily subducts. So that's a kind of a critical detail when you start getting into the details. But right now, just know that the ocean floor is very young overall. So some other people that began to looking from the subduction or the convergent side of things, so we had Hess describing how divergent boundaries work. We also then had Wadati and Benioff, two different scientists working in different areas. Wadati was Japanese, and Benioff, I believe he was American, actually. I'm not entirely sure about his nationality, but both presented evidence for deep-seated earthquakes. So we have this thing called the Benioff zone, which occurs right along the subducting plate, when a plate goes down beneath another plate. Typically, we think of oceanic lithosphere diving beneath continental lithosphere. And so because we now know that earthquakes can be shallow and deep, and we'll explore this more online, it provides evidence for subduction. You can literally watch or collect data on the earthquakes as the plates subduct beneath the other plate, and that's really powerful evidence. So you're picking up earthquakes right down along this subducting plate here as the overriding plate moves over it. And here's another example of the subducting plate, the overriding plate. This slab of lithosphere is diving beneath, and as it does so, it's rubbing up against the continental lithosphere here and causing earthquakes. So some of these earthquakes can be very deep. Actually, some of them can be several hundred kilometers deep, even though continental lithosphere isn't usually anywhere near that thick. Well, at least the crust isn't that thick. The continental lithosphere, of course, includes the upper mantle from a compositional standpoint. So, yeah, so the rigid part of the Earth is still causing earthquakes a couple hundred kilometers deep, and that's important stuff. And that's really good evidence for subduction. So as it turns out, of course, this whole picture in the modern sense is much more complicated than just this. So we certainly have divergent boundaries, like a mid-ocean ridge where plates are moving apart, and at the same time have subduction areas where plates are diving beneath others. Kind of think of it as the law of conservation of lithosphere in a certain sense, except that we are creating and destroying. Or are we destroying? Because in reality, when a plate subducts, it can subduct and penetrate deep within the mantle, or it may subduct and then sit on top of a particular layer in the mantle. There's a compositional layering within the mantle itself at 660 kilometers. So we don't entirely know how all of this works. These deflected slabs may be examples of things that cause earthquakes underneath places that aren't seismically active, like the east coast of the U.S. or something like that. And I'm not saying that that's the case, like, you know, for the earthquakes that have occurred in Virginia, but there's a lot we don't know about what's going on down here, and that's really important part. But we do know there are graveyards, so to speak, quote unquote, where slabs end up, and they don't necessarily ever melt. And so that's kind of critical. Now, the beginning of the Earth, before any of these rigid plates existed during the Hadean Eon, when everything was molten, there would not have been any plate graveyards. And so when you think about it, over the course of the Earth's history, these plate graveyards have been accumulating and will continue to accumulate. And the Earth's interior will continue to cool as the radioactivity becomes, eventually everything decays to a stable isotope. And the Earth will eventually cool off to the point where Mars or Mercury are. And the interior will be compositionally complicated because these subducting plates aren't all the same composition over time. So there's a lot going on here, and it really makes the interior of the Earth quite interesting. But for our purposes, this is getting way beyond what we need to really worry about, because we need to go back and talk about how all this works. What's the driving mechanism? Well, convection. Convection of energy within the mantle is considered to be the driving mechanism of plate tectonics. Just like you would have a convection cells build up in a pot of boiling water on the stove, likewise, as energy is radiated out from the core, which is your burner, energy is then convected in convection cells as the energy rises, and it loses energy, and it moves, of course, along the base of the lithosphere, and is eventually warmed back up. And it all continues. And so these cells end up essentially making it's actually a whole lot more complicated than this particular image makes it look very simplistic. And this is what kind of the thing that was in the textbooks when I was learning all of this. But in reality, it's a whole lot more complicated, of course. Everything always is a whole lot more complicated. These are some nice animations from UNAVCO, which is a company that studies these things. But you can see here descending plates, subducting plates, and you can also see plumes rising up. These are of course models, computer models of how things are working inside the Earth. And you have to think about this. What you're seeing here is hundreds of millions of years of time sped up significantly. Same over here. So this is not, you're not looking at what's going on. It's not roiling down there like that right now as we speak. You're looking at hundreds of millions of years of time being represented. Same here, same amount. So this is 200 million years of energy convection and transfer that you're watching going on right now in this little loop of video. So, but over that time, the way that materials move down and then back up through the mantle is very complicated. The mantle itself is considered solid, but there's a lot of material, there's a lot of movement going on within the mantle, and that's critical for plate tectonics. And by the way, critical for life, because if the outer core weren't liquid and didn't help provide some of that energy for the convection, we would not have life on Earth because we wouldn't have an atmosphere. So anyway, so what happens is slabs are pulled by these convection cells and ridges are pushed. So we consider this slab pull and ridge push. Slab pull tends to pull convections or subduction zones together, and slab ridge push tends to push continents apart. And you can see this happen over the course of 1.2 billion years of continental drift from the supercontinent of Rodinia, the breakup of Rodinia, the formation of Pangaea here, right there, and then the breakup of Pangaea to the modern day. 1.2 billion years might be a bit on the high side, probably more like 800 or 900 million years. But still, you can see that in this paleogeographic reconstruction of all that time, there's been a lot of movement that's gone on as a result of all this movement that's going on inside the Earth. So in North America specifically, we can see, of course, it's not just a matter of continents moving around, which it is. Now you're seeing half a billion years of change as Pangaea comes together and then breaks back up. But you're also seeing that other things affected, of course, is sea level. Look how sea level fluctuates over time. Why do we have carbonate limestones in the valley? Because of sea level changes. and so forth. This is a video that you could watch for a while. So I'm just going to leave it here for a bit so you can enjoy it. Really nice animation. But again, this changing of sea level and mountain building and so forth is why we have the sequences of rocks we do. All right, basically, plate tectonic theory posits that there are three types of plate boundaries, three basic plate boundaries: convergent, divergent, transform. Convergent boundaries are a result of compression. Divergent boundaries are a result of tension, the pulling apart, and then shear is what creates transform boundaries. Shear is one way of describing it. So, of course, we can look at them in the animations again. I had fun with animations this time. I didn't make all these, but any of these actually. I found them on in various places that were educational sites. So here's a nice convergent boundary. You'll see this again show up in a video that I'm asking you to watch on YouTube. And then this is a divergent boundary and then a transform boundary. All right. Well, let's start with convergent boundaries. Convergent boundaries are what create things like this beautiful, majestic alpine mountain. So you wouldn't get this, of course, this being a mountain that contains limestone on top full of fossils. If this mountain had not been part of the ocean floor at one time, but then thrust up through plate tectonic forces. And that happens by one chunk of lithosphere, in this case, oceanic lithosphere, coming into contact with continental lithosphere. And it's important to point out the difference between continental lithosphere, which is primarily granite or felsic, as we'll learn later in igneous rocks, and oceanic lithosphere, which is primarily basalt, gabbro, and mafic. So this lithosphere is much denser than the continental lithosphere, and so it preferentially descends or subducts beneath the continent. When that happens, it brings down with it water vapor, and other materials that have been incorporated in the seafloor, some of which gets scraped off in the accretionary prism or accretionary wedge, as it might make sense to you. I mean, there's definitely going to be seafloor sediment spread out, lots of metamorphism going on here. As this descends, it also causes partial melting, partially by the addition of water into the mantle, in the upper mantle, because the upper mantle is rigid, but the partial melting occurs, and materials move up buoyantly and form volcanoes. So you get the Cascade Range or the Andes Mountains, the Cascade or the Sierra Nevada Mountains, and so forth. Once upon a time, the Appalachians were volcanic. Specifically, the Blue Ridge were a chain of volcanoes. So when you drive up in Shenandoah National Park, you're driving over a lot of lava flows, the breakup of Rodinia. And so, of course, those are divergent lava flows primarily, but still it's volcanic. So it's important to point that out. That actually was a very different tectonic situation. But originally, when Rodinia came together, there would have been mountain ranges like this as well. And so the granites that are up there are the result of some of that mountain building that went on there, forming the Grenville orogeny and so forth. All right, so an example of some of what happens with this when this occurs, of course, as you might imagine, you have a big chunk of land off here. Eventually, it'll also get accreted onto we call that accretion. And accretion is something that's basically made up the entire west coast of U.S. and Mexico, and pretty much the entire state of Alaska. All these different colors are terrains that were accreted or attached onto a North American plate. Likewise, in Virginia, here we have the western Piedmont, Charlottesville, for instance, and then everything else up until the coastal plainway over here is just chunks of stuff that through subduction were accreted onto the coast of North America. And this is the Virginian part of it. But some of these extend down into North Carolina or up into New Jersey and Maryland and places like that. Because Virginia is not geologically unique. It's just the political boundary. So as you accrete, and it should make some sense that you would have stuff that kind of gets just stuck to the coastline, and that becomes part of your geologic past. So Virginia kind of actually looks like this. So we have the coastal plain. Beneath the coastal plain is a little more of this stuff over here, but you can just see how complicated the Virginia's Piedmont region is. The Blue Ridge is compositionally somewhat homogeneous, as is the Valley Ridge, but the teasing out the history of the Piedmont is much more complicated because a lot of these pieces came off of Africa, or they came off of from other places. Some of them are unique terrains, and that's Terrane, not terrain like a landscape. So we think of accreting terrains, Terrane, as a part of this whole process. So pause and take a look for a while because this is pretty interesting. All right, so during subduction, of course, in this particular case, we have oceanic lithosphere diving beneath oceanic lithosphere, and in this case, we get an island arc like Japan, or like the Blue Ridge of Virginia and Maryland and so forth used to be at one time, 300 million years ago. So here we have the volcanic front. This would be in Japan, the islands themselves. You'll also have a back arc basin sitting behind that island arc, which occurs between Japan and China over here. And then the accretionary wedge, which might produce some islands. But you'll have specifically kinds of sediments that accumulate in the fore-arc basin and in the back arc basin. And sometimes you'll even get enough stretching in the back arc to produce a divergent boundary. That does happen because the back arcs can tend to become deformed, downwarped, and thinned, and then allowing through upwelling material. But again, the subduction still produces partial melting in the upper mantle, which then produces volcanoes. All right. So here's another representation of the same thing. Essentially, we can watch through a fly-through animation of the seafloor.
Geologist at Oregon State University, and then co-chief scientist on this expedition. This is what the seafloor around the Mariana region looks like. The deepest depths are the purples and blues. In the foreground on the right is the Mariana Trench, the deepest part, and the shallowest depths are yellows and reds, and green is above sea level, so those are islands. In the middle right, you can see the island of Guam. We're going to fly along the Mariana back arc, which is this white line. So this is what it would look like if you could see through the ocean and you see the seafloor. The Mariana back arc is where the upward plate here is spreading. So the part to the right is moving to the right, the part to the left is moving to the left, causing the hydrothermal events that we're hunting for. I'm Bill Chadwick. I'm a geologist at the seafloor.
So I'm just going to point out a couple of things here. This is your fore-arc region where the trench is, the actual Mariana Trench. You're all familiar with the Mariana Trench because it often discusses the deepest place of the ocean. So here's the islands that include Guam and so forth. And then the back arc area, which in this case is a spreading center. So this is the typical, a very typical structure or sequence of structures for a volcanic island arc. All right, so you can have in convergent boundaries, like I just pointed out, oceanic to oceanic, or oceanic continental convergence, like the west coast of the United States, specifically the northwest, Pacific Northwest, and on up into British Columbia. You can have oceanic and oceanic convergence, like Japan or the Philippines, and then you can have continental. This is like the Himalayan plateau, essentially, where India has slammed into Asia over here, or in the case of the Arabian and the Eurasian plate here. So again, you have plenty of examples of all three types of convergent boundaries, basically where two continents are coming together, or two plates are coming together. Divergent boundaries are literally places where the plates are ripping apart. And this is an example of that's near and dear to my heart because actually it was I was in Kenya a year ago. That would be early January of 2018. My wife went there a few months later, right after this crack opened up in the middle of the Rift Valley through Kenya, and actually right across this road, which is the main highway that connects the smaller city of Narok from the larger city of Nairobi. And it takes about 4 hours to drive across this road. And normally, you only travel about 45, 50 miles an hour at most. It's pretty dangerous driving in Kenya, actually. But this crack opened up as a part of the whole divergence that's going on over there. And you can see a lot of unconsolidated sediment. It's all volcanic sediment. So still active volcanoes throughout the Rift Valley. But you can see over here, this is actually one end of the, so that you were here in the valley, and then this is outside the valley. This is the the Graben region. Or I'm sorry, the Horst region. We're in the Graben here in the valley, and the Horst over here on the one side is. And if you were to look over here on the far left, there'd be another Horst. So as you traverse the valley, this crack opened up. They got it filled in before my wife had to drive over the road, fortunately. But this is what happens. Here's your Rift Valley, and then there's one side where Narok is and one side where Nairobi is. But what's happening is they're spreading apart, bounded by normal faulting, which we'll talk more about later in the semester. But one block of this drops, that's the Graben, while relativistically speaking, the Horsts move up. And so here's a great example. The classic example, of course, is the East African Rift region, which includes not just the East African Rift down through Ethiopia, and of course also the rifts in Kenya, Tanzania, and on down, but also the Red Sea and the Gulf of Aden, which are two other rift zones. You can actually see the rift zone here and see the rift zone here. This rift zone extends up through the Sinai Peninsula and up in through Israel as well, as you can see up through here. And the Gulf of Aden also connects eventually to the Indian Ocean and a series of rift or mid-ocean ridges over there, that major ocean. But you can see also that the rift zone moves further south. So if we look at the different stages in the development of a rift valley, where you're ripping continent apart, this part of the rift valley, before you even really have ocean flowing into it, maybe just a river, is right down through here, and it continues on through East Africa. Eventually, they'll spread open enough to potentially produce an ocean basin, in this case, a new ocean basin, like in the Red Sea and the Gulf of Aden. And then mature ocean, which is like the example of the Indian Ocean over here, takes much more time to form. But Africa and the Arabian Peninsula are moving away from each other physically, and that's how rift valleys work. And they typically occur in threes as well. So you've got one rift, two rift, third rift, and that's very common. And of course, as rift valleys open up, as we already talked about, you get the magnetic reversals that happen over time, and they leave that magnetic striping on the seafloor. And in between the rifts, there'll be chunks of rift bounded by transform faults, which are necessary to allow for the curvature of the Earth. And that's pretty critical. So transform boundaries, let's bring those into focus now. Transform boundaries are places where the crust moves and slides past itself. So you can have sinistral and then dextral, or right lateral and left lateral strike slip faults or transform boundaries. And of course, these can be major earthquake zones as well. San Andreas is an example of a transform boundary. Here's the San Andreas. Of course, they're just hearing on the news this morning about what would it be like to have a 7.5 or a 7.8 down here in the LA region, and how horrible that would be. Of course, these faults or these transform boundaries are not perfectly straight boundaries. So you can have situations in them where you get restraining bends or releasing bends, which of course can form little mountain ranges in their own right, and of course also accentuate or make even more problematic the seismic challenges that occur in these areas. This is a nice video that talks about the tectonic history of Western North America and Southern California. So I'll go ahead and play that for you. As you can see, this Juan de Fuca subduction zone, which we know occurs in the Pacific Northwest, has been subducting beneath North America, which ends up forming the San Andreas Fault, leaving a bit of it up here and a bit of it down here in the Gulf of California. If we watch that occur again, you can see what it does. It actually ends up stretching out, essentially, the western part of North America as that subduction occurs. So the basin and range of Nevada, the stretching is a result of the stretching of this crust in the back arc basin. So of the subduction. So if we look at that video, I'm going to go ahead and bring it up here and just pause it, I think. It'll let me. Now, Nevada is often described as a place where you could have a rift open up, and that's why. All right, so this all brings together all these three things together: convergent, divergent, transform boundaries. Describe the situations that exist in terms of continents moving around. And as you've seen, the Atlantic Ocean has opened and closed and opened and closed. What we think of as the Atlantic Ocean has had different. We give it different names depending on the time: Iapetus, so forth. So continents drift apart and back together, and there's a cycle to that we call the Wilson cycle, or the supercontinent cycle. And this is what this looks like. So Rodinia was a supercontinent. There were more supercontinents before Rodinia that have similarly colorful names. Pangea, and eventually we'll start, the Atlantic will close again and form another supercontinent. And that's really important. So this is named after another important person in the development of plate tectonic theory, J. Tuzo Wilson, who is a Canadian geologist. Finally, hotspots. Another good piece of evidence for plate tectonics are these. These are plumes of mantle material that make their way up somewhere near the core mantle boundary and are stationary, and so they don't move while the continents do move. And they'll form things like the islands of Hawaii, which you're all familiar with, and they all have this sort of linear fashion to them, the big island being the most volcanically active, and the subsequent islands to the northwest being more ancient as you go on. So the big island's the youngest. The last island you see protruding over here is the oldest. As you continue on, you have the Hawaiian seamount chain, and then the Emperor seamount chain. This is interesting bend over here that occurs 45 million years ago, and that is where India slammed into Asia. And when that happened, it actually caused a rotation of the Pacific plate. And that's what's going on here with this bend. But this hotspot has been here under Hawaii, or under this particular location on the globe, for the entire time, producing these seamounts and so forth. Similarly, Yellowstone National Park is a hotspot, and you can see as that hotspot, as time has progressed, how that hotspot has moved. And once upon a time, it was over here in southern Oregon, but it's since moved up through the valley here, which is actually what forms the valley, largely to where its current position here in Yellowstone National Park. We know, of course, there's been major eruptions of Yellowstone that we can date the ash beds from. And so we have some idea of where the ash beds began and just how extensive they really were. Quite an eruption it'll be one day when it does erupt again. Okay, so that's plate tectonic theory. There's a lot to think about there, but again, to summarize it, we're looking at how the Earth's plates, lithospheric plates, how the continental plates and the oceanic plates work together to produce subduction and divergence, and how the Earth, when the Earth doesn't change its shape or change its size, changes over time as these plate boundaries do their thing as a result of the convection, radiation, and then convection going on within the Earth. So anyway, we'll deal with more with this online or possibly in class. But in the meantime, just study the material and become pretty familiar with it. Okay? Have a great afternoon.